Hello everyone, this is section 10.4. I'm going to do a brief video and I will make every effort to keep it brief. I just wanted you to have some sort of instruction while I was out for the day. There are two tests in this section. One is called the divergence test and the other is called the integral test. Now at this point I like to pull up the series chart, our little cheat sheet, and I'll be doing this throughout the video. Our divergence test is right here. It's this top one called the nth term test. It has a couple of different names. Our book calls it the divergence test, and that is because it only tests to see if something diverges. It does not test, I repeat, does not test whether or not something converges. But the reason that it's really handy is because it's a simple limit calculation. If you calculate the limit of as n approaches infinity, and you find out that the limit is not 0, then you know automatically that the series diverges. And that means you can stop. Okay, now if you find out that the limit is 0, then that's inconclusive. We have to try a different test to prove convergence. Okay, so going back to the notes, I think we all know, does something converge? If the answer is no, then the series diverges and we're done asking questions. If the answer is yes, then the series converges, and it might be that we could estimate what value it converges to, or to which value. Forget it. So looking at the divergence test, it's a pretty simple test. You take the limit, and our sheet says n, our book uses k. You take the limit as n or k approach infinity of the actual expression in the series. And if that limit is 0, then we might be able to say something, we might not be able to say something. But what we do know is that if we know a series converges by another rule, then that limit is going to be 0. Now, if the limit of the sequence is not 0, then automatically we can say the series diverges and be done with the problem. The important note, of course, is that theorem 10.9, the divergence test, cannot be used to conclude that a series converges. And again, that's what you're seeing right here with the blank box. We have no way of using this particular test to determine convergence. So let's take a look at a couple of examples. It says determine whether the following series diverge or state that the divergence test is inconclusive. So if I look at the first one, letter A, now this one is one where you have to know your horizontal asymptote rules. The degree of the numerator is the same as the degree of the denominator. So this converges, or the limit, is the leading coefficient over the leading coefficient, which is 1. And if we go back and we look at our series chart, the limit is not 0. It is not 0 because it is 1. So it diverges. Okay, I'm going to skip B for a minute. I'm going to go to C. Now this can also be used with horizontal asymptotes. The degree of the numerator is 0, and the degree of the denominator is 1. It's bigger, it's bottom heavy. So when that happens, we get a limit of 0. And so look at our decision-making tool. The limit is 0. So there's no conclusion that we can make. Okay. If we do the same thing with D, we get 0 again by the same rule. Has a horizontal asymptote at 0. Okay, now I saved B because B is sort of looking a little bit geometric. We really don't know how to handle B just yet. I'm going to pull up the notes for that problem. Let me scroll real quick. I'm running out of space to write. Sorry about that. Hope I'm not making you dizzy. Okay, so here is B, and what they're going to do is bring up this 2 to the k into the numerator. Okay, so when we bring it up from the denominator to the numerator, that exponent of k is going to become negative. And I'm going to go try to find some space here. Let's go all the way down to the bottom. So the limit as k approaches infinity. I'm going to bring that 2 to the k up to the numerator. And then I'm going to maybe distribute it, see what happens. So I'll have 2 to the negative k times 1. And I don't know what this is going to be because they don't have the same base. Hard to say. Now, what's going to end up happening, though, is as k gets really big, right, as k gets really big, if k were down here, you know that might go to 0, okay? Now, if you look at what they're doing here, they're taking this 2 to the negative k, and they're putting it back down in the denominator now that they have it split up. Which makes sense. I mean, you could have done this a different way, and I will do it a different way. You could have just split this fraction up. The way I did it might have been a little awkward. So 1 over 2 to the k plus 3 to the k, whoops, it's an exponent, over 2 to the k. Now you've got two situations going on here. As k goes to infinity here, this is going to approach 0. That's pretty straightforward because the denominator is much bigger than the numerator. But this one is actually a geometric sequence, and it is legal to take the 3 divided by 2 and raise those to the k power, and that is because we are dividing. So this one is geometric, and we've already talked about the geometric sequence. Our r is 3/2. That's the thing that we're multiplying by every time. So if you go back over to the series chart and you look at the geometric series, if r, the absolute value of r, is greater than 1, then that diverges. And if you think about this mathematically, just numbers, 3 over 2 is bigger than 1. So every time I multiply by another 3 over 2, I'm going to continually get a bigger and bigger and bigger number. So in essence, what is happening with this is going to infinity. And by the geometric test, we know that this diverges. So I prefer to think of this one as it diverges because one piece of it diverges. I'm not sure if the book is going to do it that way. Let's take a quick look. Yeah, they basically said, hey, the whole thing goes to infinity. And so it diverges because the limit is not zero. And that makes sense to me. Like, if you think about the limit, we want it to be not equal to zero. Because if it is not equal to zero, then it diverges and we're done. Okay? So that is what, and I'm not going to do a whole bunch of those because they're basically that way. Before I go on to the integral test, I want to talk with you about a special series that we just saw in that example. And that is 1 over k, or depending on what variable you're using, it might be 1 over n. And we call this the harmonic series. I didn't name it. I didn't have any part in naming it. But this is one that you want to remember. It's going to come up a lot in the following sections. Okay, so you want to remember that the harmonic series is this. And you want to remember that it diverges even though the terms of the series approach 0. This is a special case. Okay? So the limit is 0, which makes it inconclusive. But in doing some different kind of analysis, we can take a look at what's happening, and that is not converging. You can also take a look at a numerical chart and look at the partial sums, and those numbers keep getting bigger and bigger. So there's a lot of theory involved in the harmonic series. I'm not expecting you to justify it. This is something that you can remember as a fact and use it when it's convenient. Okay? Now, last thing, integral test. This is the thing that people kind of dread because you actually have to integrate. Now, the integral test is a test to determine whether, yes or no, does it converge, does it diverge? Okay? But there are some conditions that have to play out. So I'm just going to read it. Suppose f is a continuous and positive and decreasing function for x greater than or equal to 1, because we start at 1. And let a sub k equal some function. So whatever this is, a sub k, it's going to be some sort of function. And it's going to be starting at 1, go on and on and on to infinity. Then either this series and this integral converges, or this series and this integral diverges. In the case of convergence, the value of the integral is not what the series is converging to. Okay? So if you take a look at our chart, because I always want to go back to the chart, I want you to get used to using it. Integral test says f is positive, continuous, and decreasing. You do not have to memorize that. Okay? This is describing that a sub n is your function. And you are going to integrate that function once you know that you've got these 3 things in place. Because if you don't have these 3 things in place, you can't use this test. So once you decide, hey, all those 3 things exist, then you're going to integrate it. And if the integral converges, then the whole series converges. If the integral diverges, then the whole series diverges. And this is one of those very rare situations where we actually visit previous units in Chapter 10. It doesn't happen very often in Chapter 10. So indefinite integrals with the infinity, we have to deal with that. Okay? So let's take a look at an example. Let's see which example we want to do. That's u sub, that's u sub. That's inverse tan. So I'll just pick one of them to do for now. Now, in looking at this, none of these look geometric to me. And none of them if I take the limit of them, like apply the divergence test, I might get 0. It's hard to say. I think with all of these, actually, I'm going to get 0. Yeah, I'm going to get 0. So all of these are inconclusive. There's no way to know by the divergence test that we can stop. Okay? So if I look at A, and I'm like, okay, divergence test doesn't work. It's not geometric. You know, there's other things we've talked about. But I'm going to try the integral test. And I'm going to think, okay, are all of the terms positive? So if I take the expression and I write out, I'm going to write out the first couple of terms. That's going to be 1/2. Write out the second term, plug it in a 2. That's going to be 2/5. I write out the third term, and I could keep going for a while, but I think you guys are probably getting the idea that these terms are all positive. And the reason that they're positive is because in the numerator, k is always a positive number. It starts at 1. In the denominator, it is always positive because we're squaring a positive number and adding 1 to it. So you will never get a negative number with this expression. And that is actually true for all 3 of these. So I'm going to say yes. And then I'm going to say, is the a sub n continuous? So what I do with these is I look at the denominator. Can my denominator ever be 0? From 1 to infinity, where k is 1 to infinity. And when I look in the denominator, I see k squared plus 1. There is no chance that that denominator is going to be 0 because there's no negative 1 to offset the 1 in the case of the k squared. So we can say yes. And we don't really have to do a whole lot there, okay? Now the last characteristic I need, let me scroll just a little bit, is it has to be decreasing. This can get a little tricky because if you can't tell what your series is doing, then you have to go back to Calc 1 and perform the first derivative test for decreasing. In a lot of them, you'll be able to tell that they're decreasing. So let's take a look at ours. My first term was a 1/2. My second term was 2/5. And then a 3/10. And obviously this would keep going. But if you look at the value, I like to go out a few terms. Can you guys see that it's decreasing? And so that is enough. But on a test, before using the integral test, you have to demonstrate all 3 of those. It is not enough to just look at it and go, okay, I'm going to integrate it. Because technically, the test does not hold true if you do not have all 3 of these things happening. Okay? But now that I have all 3 of them, I'm going to integrate. And I'm starting at 1 because my series starts at 1. If I were doing B, I would start at 3. If I were doing C, I would start at 0. I just follow what's written in the problem. And I'm going to change those things to x's. You can leave them as k's. It does not really matter. I just prefer x, and a lot of you guys prefer x. So the way that you handle these, I don't know if you remember, but we introduce a limit. And the limit variable that you're using, a, b, whatever, takes the place of the infinity. And then at the very end, we take the limit of what we get after we integrate. Okay, so in this situation, I'm going to do a u substitution. making the denominator my u. And you can see that I have that x dx right here. Okay, so that du over 2 is x dx. But remember, when I do u substitution, I also have to change my bounds. So my first u is going to be 1 squared plus 1. And my second u is going to be b squared plus 1, which is just b squared plus 1. So let's set up our integral. We'll have 2 to b squared plus 1. I got to write in my limit over here. And then I will have, where am I going to put the 1/2? Let me make some space for Mr. 1/2 there. I'm going to take that 1/2 all the way out. B squared plus 1. And then we will have 1 over u du. Right, this x dx is my du. What's left is a 1 in the numerator divided by u. And I'm hoping that you guys all remember that that's natural log when you integrate it. Now, as far as absolute values, in many of these situations with natural log and series, you won't need them because you're plugging in positive numbers. But I put them in just for the first iteration of this, and then I'll drop them in a moment. Okay, so plugging in my upper bound, minus my lower bound, I'll have natural log of b squared plus 1, which is positive, minus natural log of 2. Now I have to apply the limit. So I have to look at these and go, okay, this one's not going to be impacted by taking the limit as b approaches infinity, because there's no b in it. This is a constant. So this is just natural log 2. Now what's going to happen here is, and this is kind of awkward, but I'm going to have this, infinity squared plus 1. And we have to think, what is the natural log doing? Right? What's going on with that? This is going to go to infinity. And then, you know, we got the 1/2 out here. So because it's going to infinity, minus natural log 2 times 1/2, the infinity is what's going to cause us trouble. And this is going to be a diverging situation because we did not get a real number when we took our integral and applied our limit. So let's see real quick. Let's take a look at the book solution. So there's me. That's what I had done. This becomes infinity. And they're reminding you of that, right? They're doing that right here. And because the integral diverges, the series diverges. Okay? And that is the gist of the integral test. It's not the test that people really look forward to doing. But instead, what we typically do with this test is we try to do anything easier first. Like, is it a p-series? Is it geometric? Could we say it diverges from the divergence test? Is there anything else we can do? And if there's not, then we investigate the integral test. And it helps that all three of those problems, let me pull those back up. It helps that all three of those problems actually do integrate, because that is a clue that you can perhaps apply the integral test. I'm just going to show you the results for the other two briefly. There's that one. They're going to perform U substitution on that. Let's see. It says the integral test may be modified to accommodate initial indices other than 1. So see how they've started with 3. And they performed a U substitution here. Okay, let me show you the inverse tangent one. And I am very sorry, this is an inverse tangent one. This is one of those situations where trig is not prevalent, but it's always a possibility. An inverse tangent is oftentimes one of the ones we see the most frequently. So if we integrate this with U substitution, we get 1/2 tangent inverse x over 2 from 0 to b. And what's going to happen is, and this is where people get really angry, they don't remember what the tan inverse looks like. So this is why I kind of wanted to pull this one out. Tan inverse looks like this. And so if this is my b, and my b gets really, really big, even if it's divided by 2, this has asymptotes at pi over 2 and negative pi over 2. So this is going to approach pi over 2 for this first part. Now, tangent inverse of 0 is just 0. Because at that point on the unit circle, tangent is 0. And people are usually not very happy when I pull out the inverse tangent problems. So if I were to, and let me show you how they get to pi over 4, they would have 1/2 times pi over 2 minus 0, which is pi over 4. And because that is a firm number and not infinity, then the integral converges, therefore the series converges. We don't know what it converges to. It's not pi over 4. But the fact that we got a number and not an infinity means that it converges. And we can say that with authority. Okay? Let's see. Now the P series, I just want to go over this very briefly because at the time that I'm making the video, I honestly can't remember if I have covered this in 10.2 and 10.3 or not. So I'm gonna cover it. If we've covered it, you can just turn off the video and skip it. The P series is a really great test, but it has to be in the form 1 over k raised to an exponent, or it has to be in the form 1 over n, if we're using the n variable, raised to an exponent. And what is going to happen is this P is going to be a number. And the way the P series test works, and this is so convenient, if the P is greater than 1, then the series converges. If the P is less than or equal to 1, then the series diverges. So on your P series test, you'll see they're giving you the format, and they're using n instead of k, raised to the power of p. Here's the converges column. If p is greater than 1, it converges. If p is between 0 and equal to 1, it diverges. And if p is 1, then this is the harmonic series that we spoke about a little bit ago. Okay? So let's take a look at a couple of examples. And some of these might kind of be disguised. So let's rewrite them. I'm going to move that k to the -3 down to the denominator. And hopefully you can see the p. You can see that it's 1 over the variable, which is raised to some number. That p is 3, which is greater than 1, so it converges. It's that simple. It makes the integral test look ridiculous by comparison. And remember, p greater than 1 is in the converging column. I'm going to write b a little differently. Let's see, that's going to be k to the 3 over 4. Remember how to handle your rational exponents. Your p-value is 3 over 4, which is less than 1. So this diverges. It's literally that simple. Okay, now this last one doesn't look like a p-value at all. I mean, kind of does. Now, if I expand that, this is where we talk about the degree of the denominator. That degree of the denominator is 2. And that k squared term is going to dominate everything. Okay, it's going to outweigh the 2k and the 1. So we call this a convergent p-series with p equal to 2 without the other two terms. And it says, recall that adding or removing a finite number of terms does not affect the convergence of the series. Why is that? Because the 2k and the 1 are much, 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 much smaller than the k squared. So this is going to behave like 1 over k squared. And what I like to do at this point, and I am almost done, guys, what I like to do at this point is put them in the calculator so that you can see that. I'll use x, though. Okay, so there's your 1 over x squared. They're behaving very similarly. The only difference is a shift to the right, 1 unit. So can you tell that the behavior of the second one, which is our problem, looks very much like the behavior of the red one, which is just our problem without the other two terms that are much, much smaller. And that is legal to do, by the way. You can look at your dominant term. I'm going to give it a little circle here. This term is the one that's your dominant term. So it is driving the behavior of that function. Okay? So that is your 10.4. Thank you, and I will see you next class.